Hello dear students, I am Dr. Moinuddin. Students, in this video we are going to discuss about inductively coupled plasma atomic emission spectroscopy. And this is the part 2 of this technique. In part 1, we have discussed the basic introduction of this technique together with the principle of operation. So if you didn't watch that video yet, then I'm attaching its link in the top right corner, so you can find it in the I button. And here are the contents of current video. So in this video we are going to discuss about the design and construction of plasma torch. So how does it look like? Then we'll see the nomenclature of ICP, in which we'll learn about different zones of plasma, and then in the end we'll see the various components of inductively coupled plasma system, that is different components which are used in ICP-AES. So we will discuss those components in the end. So you need to watch this video till the end so you can better understand this. So let's start with plasma torch. Plasma torch is made up of quartz, and actually it is not a single quartz tube but 3 concentric tubes. So in plasma torch there are 3 tubes which are made up of quartz, and these are concentric, means having same center. So you can see here are the diagrams, 2 diagrams on the top and bottom. So if we see this diagram, so this is the outer tube, then this one is the middle, and this one is the inner tube. So these are the 3 tubes which are made up of quartz. So same you can see in the bottom, which is clearly shown over here. The high temperature of plasma requires protective isolation from quartz walls. As we have seen earlier that the temperature of plasma reaches up to 8,000 to 10,000 Kelvin. So this temperature is too much high that it may deteriorate the quartz tubes. So we need to keep this plasma separated from the tube. So how it is done? So it is accomplished by a tangential flow of a coolant gas between 2 outer tubes at the rate of 15 liters per minute. So to keep plasma separated from the tubes, a gas which is definitely argon gas, and it is called coolant gas, and it is made to flow in the between the 2 outer tubes, you can see over here, and it flows tangentially like this. So argon gas that is made to flow tangentially between the 2 outer tubes. And what is the rate of the flow of this gas? And that is 15 liters per minute. Means in 1 minute 15 liter gas passes through these between 2 outer tubes. And what is the purpose of this gas, which is called coolant gas? It isolates plasma from the torch walls, as I mentioned earlier, because the temperature of the plasma is much higher, so we need to keep it separated. So it isolates plasma from the torch walls, stabilizes and centers the plasma. So it keeps plasma separated from the quartz tube, and it stabilizes and give it the proper shape. So this is the function of this coolant gas. And this protective technique, this is also known as Reed's vortex stabilization technique. Another gas which is called an auxiliary gas, or it is also known as plasma gas or support gas. This gas is used during ignition of the plasma. And where does it found? It flows between 2 inner tubes. So we're talking about this one and this one. So This auxiliary gas, plasma gas or support gas, actually it flows between two inner tubes, or if we number the tubes, then the outermost is called 1, then the middle one is 2nd, and the innermost is the 3rd one. So actually this auxiliary or plasma gas flows in between the 2nd and 3rd tube, and this gas is used during ignition of the plasma normally. And what is the rate of the flow? So it is made to flow at the rate of 1 to 5 liter per minute. So this gas, actually it flows over here at the rate of 1 to 5 liter per minute. And let me tell you that this gas is also argon gas. So but it has different name over here and different purpose as well. Then the 3rd gas, so a small diameter central tube is used to introduce a sample. So we are talking about the innermost tube. So definitely the diameter is the minimum as compared to the rest of the tubes, and this tube is used to introduce the sample into the plasma. And how the sample is introduced? So sample is introduced usually as a fine liquid aerosol, as usually the sample is introduced and that is in the form of solution, and the sample is introduced by the use of carrier gas. So here is the sample which is introduced with the help of a carrier gas, and this carrier gas is again argon gas. So it takes sample through this innermost tube and enters into the plasma, and the rate of flow of this carrier gas is 1 liter per minute. So these are different gases which flow through these different 3 concentric quartz tubes. Careful design of torch enables the sample carrier gas to penetrate the base of the plasma. So carrier gas carries the sample and enters the base of the plasma. Then the hot plasma is toroidal. This is actually we're talking about the shape of the plasma, and sample experiences central channel. So sample enters the central channel where temperature may range in 5000 to 8000 Kelvin, which is too much high temperature. Then during a transit time of 2 to 3 millisecond in this channel, so it takes only 2 to 3 millisecond that the sample stays in this channel of plasma. So during this time the sample aerosol is desolvated, volatilized, mean the sample is evaporated due to a very hot plasma. Then it is dissociated, means if there are some kind of bonds, so bonds are broken and the components are separated from each other, and the sample is atomized. They are converted into gaseous atoms, and there are chances that they may be converted up to some varying degrees. They may be ionized, that some of the atoms they may also be converted into ions by losing electrons. But actually we are interested in the gaseous atoms, and these gaseous atoms, free atoms, these are then electronically excited, mean they take energy by the heat of the plasma and they get excited. Actually the valence electrons get excited and then they de-excite and giving the different radiations. And these electronically excited atoms, soon they return to the lower energy levels, and generally these occur within the nanosecond period of time. So they return back to their ground state level by emitting radiations of different wavelengths, and these wavelengths fall generally in the region of ultraviolet and visible region. The wavelength of this emitted radiation is the characteristic of atomic species present in the plasma, And this is actually the characteristic of each and every element. Mean an element when gets energy in the plasma or flame, it is excited always in the similar states, and definitely when it will return back, so it will produce radiations of same wavelength always. Mean it become the fingerprint of that element, and due to these radiations we get peaks, we get spectra, and so for the same elements we get same peaks at the similar position, and this becomes actually the qualitative analysis of that element. So we can guess that which element is present in the sample, while the intensity of emitted radiation is proportional to their quantities. And what is the peak height? This tells us actually the intensity of emitted radiation. More the intensity, greater will be peak height, and this is actually proportional to their quantities. Mean from the intensity of emitted radiation we get the quantitative analysis. So in this way, this technique provides us both the qualitative and quantitative elemental analysis. So we can perform a complete analysis that which elements are present in our sample. So this was all about the design of the torch, and now we will see the nomenclature of ICP. What does nomenclature mean? Actually, the plasma has been divided into different zones. So we'll see these zones and how these zones are divided actually, because they are happening different events, and they have different temperature ranges. So on this basis, so plasma is divided into different zones. So now let's see these zones. So inductively coupled plasma has distinct structure, and a nomenclature system has been derived to describe the zones of plasma. So first zone is the initial radiation zone. It is present low in plasma. So this is present low. So here is the plasma, and this is the preheating zone where volatilization, dissociation happens. And then above this one, this is the initial radiation zone, and where it's present at the height, you can say 0 to 10 millimeter or 0 to 0.4 inch above the induction coils. So here are the induction coils. So the distance measurement starts from here. So from here 0 to 10 millimeter, or in inches it is 0 to 0.4 inches. So this region is called initial radiation zone. And what happened over here? Usually atomic emissions are observed over here. So this event occur here. Then there is next zone, which is called normal analytical zone. So vertically higher, this region exists, which is most commonly used for spectroscopic measurements, together with some ionic emissions too. So it is present vertically higher on initial radiation zone, and this is commonly used for spectroscopic measurements, in which we observe different emissions, and there are also some ionic emissions too which are observed in this region, and this region exists over here. And what is the actual height where this region exists? So it extends approximately 10 to 20 millimeter or 0.4 to 0.8 inches above the induction coil. So if we start measurement from this induction coil, so from 10 to 20 millimeter, we can say somewhere here it exists, the normal analytical zone. Then if we talk about the third zone, that is called tail plume region. So still higher, the tail plume of the plasma is found somewhere here, and where it actually exists, so it extends from 30 to 100 millimeter or 1.2 to 4 inches above the induction coil. So it is present on the top, so it is actually the topmost part of the plasma, which is called tail pallium region. And what events does occur over here? Some atomic and molecular emissions, actually these are observed over here. Then these zones differ from each other with respect to temperature as well. So temperature is moderate, around 5000 Kelvin in the lower zone, which is called initial radiation zone. Then it reaches maximum around 6000 to 8000 Kelvin in the middle zone, which is called normal analytical zone. And then temperature drops rapidly around less than 5000 Kelvin in the tail pallium region. So as temperature gradient exists in plasma, mean temperature drops in different regions in plasma, so different elements reach their maximum emission intensity at different heights, which is actually their characteristics, that some elements are easily excited and while other are not. So they show emissions in different regions of this plasma. So different elements reach their maximum emission intensity at different heights above the induction coils according to difference in excitation energies of different atoms and ions, as I mentioned earlier. So in this way, simultaneous multi-element analysis can be performed. So we can analyze more than 70 elements at a time, which is a great advantage of this technique. So this was all about the nomenclature of plasma, and now we will see the various components of inductively coupled plasma atomic emission spectrometer. So the principal components of an analytical ICP system are, so there must be the sample introduction system, through which by the use of that the sample is introduced into ICP-AES. Then there will be the ICP torch and various argon gas supply system. Then there will be the radio frequency generator and associated electronics. Then there will be present the spectrometer, then the detection electronics, and then there will be the system computer to get the result in the form of spectrum on the screen of computer. So these are different components of inductively coupled plasma atomic emission spectrometer. In this slide we can clearly see the relationship among these various components, which are shown in the form of this flowsheet diagram. So we can see here is the sample which is being introduced by the use of some carrier gas into this sample introduction system. So here are the gas supplies. So here is the carrier gas which is used to introduce the sample into this system, and by use of this gas the sample is introduced into plasma. And here are some other gases like coolant gas, auxiliary gas, which are used for the generation of plasma and to keep it separated from the quartz tubes. Then here is the radio frequency generator, and what is the function of this one? I have explained it earlier in the part 1, so you can watch it. That what is the role of radio frequency generator for the production and sustenance of the plasma. Then sample comes into the plasma, and there are volatilization, vaporization, atomization, excitation, and emission of various lines, which are sent to the spectrometer, which senses these lines, and there are detectors which reads the wavelength, and all the data is sent to the computer, which shows us a result in the form of spectrum. So next in the next video actually we'll see all of these parts in complete detail. So dear students, this was all about today's lecture, but hope you did understand it well. So if you like it, then like my video, but the technique is not over yet, so you need to stuck on my channel. So if you didn't subscribe my channel yet, then subscribe it right now, so you can get in touch with my upcoming videos, upcoming next parts relating this technique. So thanks for watching. Thank you very much.